Welcome to today's video, where we are diving into the fascinating world of muscle contraction and exploring an intriguing concept known as the tension surface model. Before we are going into the mechanics of muscle contraction, let's first understand the concept of surface tension. Surface tension is a property that exists not only in liquids but also in jelly-like materials like our muscle fibers. It plays a pivotal role in how myosin and actin threads interact. And this understanding will be the key to unraveling muscle contraction. To understand muscle contraction, we first need to know a bit about the anatomy of skeletal muscles. These muscles consist of smaller units called muscle fibers. Muscle fibers are made up of even smaller structures known as myofibrils. And when we zoom in further, we discover that myofibrils are composed of two types of threads, myosin and actin. Myosin threads are about 160 angstroms in diameter, while actin threads are much thinner, at around 50 angstroms. These threads align in a precise pattern within the myofibril, allowing them to slide past one another during muscle contraction.
Now, let's talk about how muscle contraction actually occurs. It all begins with an electrical nerve impulse. This impulse triggers the release of calcium ion into the myosin-actin structure. This calcium ion causes conformational change leading to the sliding of myosin and actin thread which shorten the entire myofibril. This collective sliding of thread is what we observe as muscle contraction. The muscle gets shorter and pull on its attachment point.
Now, here's an interesting idea. This surface motion be responsible for this contracting motion. This is known as the surface tension model.
Some researchers have suggested that the force driving muscle contraction may be similar to the way liquid move due to surface tension. Think of it like the capillary movement of a liquid.
It proposed that the attraction between surface of myosin and actin thread could be triggered by the release of calcium ion, but remember, this is a simplified model and doesn't capture the full complexity of muscle contraction.
Now let's get into the calculation. To estimate the force generated by the surface tension, we need to determine the number of threads per square centimeter. The formula for this is n equal to 1 divided by pi divided by 4 and multiplied by d square, where d represents the average diameter of threads. This formula allows us to find out how many of these tiny threads are packed into a 1 square centimeter area. Once we have the value of n, we can proceed to calculate the maximum pulling force on each fiber. This is done using the formula F equal to pi multiplied by d multiplied by t, where pi represents the mathematical constant pi, d is the average diameter of the threads, and t stands for surface tension. And how can we calculate the total force? To determine the total maximum force within muscle tissue, we multiply the force calculated for each individual fiber by the total number of threads in a 1 square centimeter area. For example, suppose we have calculated the maximum pulling force on each fiber to be 100 dyn per centimeter square, and we have determined there are 10,000 threads in a 1 square centimeter area. The total force can be found by multiplying F by n, so that we're gonna get 100 dyn per centimeter square multiplied by 10,000 threads. Total force is gonna be equal to 1 million dyn per centimeter square. This example calculation demonstrates how to find the total maximum force due to surface tension within a 1 square centimeter area of muscle tissue.
Now, let's compare our calculated surface tension force with the actual measured force capability of muscles, which is around 7 multiplied by 10 power 6 dyn divided by centimeter squared. As it turns out, a surface tension of 1.75 divided by centimeters can account for this measured force, suggesting that surface tension might play a role in muscle contraction. However, it is essential to remember that muscle contraction is incredibly complex, and this model is a simplified representation.
To sum it up, we have explored the basics of muscle contraction and touched on the surface tension model, which offers an interesting perspective on how muscles work. Keep in mind that while this model has its merits, the true nature of muscle contraction involves a lot more intricacy that researchers continue to study. Thank you!